study how to determine Young's modulus of the material of a wire. A typical experimental arrangement to determine the Young's modulus of the material of wire under tension consists of two long straight wires of same length and equal radius suspended side by side from a fixed rigid support. The wire A, called the reference wire, carries a millimeter main scale M and a pan to place a weight. The wire B, called the experimental wire, of uniform area of cross section also carries a pan in which known weights can be placed. A vernier scale V is attached to a pointer at the bottom of the experimental wire B and the main scale M is fixed to the reference wire A. The reference wire is used to compensate for any change in the length that may occur due to change in room temperature, since any change in length of the reference wire due to temperature change will be accompanied by an equal change in experimental wire. Both the reference and the experimental wires are initially less load, and slowly load is increased to keep the wires straight and the vernier reading is noted. The difference between two vernier readings gives the elongation produced in the wire. Let R and L be the initial radius and length of the experimental wire respectively. Let M be the mass that produced an elongation delta L in the wire. Thus, the applied force is equal to mg, where g is the acceleration due to gravity. The Young's modulus of the material of the experimental wire is given by Y equals stress by strain, which equals mg multiplied by L whole divided by pi r square multiplied by delta L. Let us have an example. A steel wire of length 4.7 meter and cross-sectional area 3 multiplied by 10 to the power 5 meter square stretches by the same amount as a copper wire of length 3.5 meter and cross-sectional area of 4 multiplied by 10 to the power minus 5 meter square under a given load. What is the ratio of Young's modulus of steel to that of copper? Let us have the solution. Length of the steel wire L1 equals 4.7 meter. Area of cross section of the steel wire A1 equals 3 multiplied by 10 to the power minus 5 meter square. Length of the copper wire L2 equals 3.5 meter. Area of cross section of the copper wire A2 equals 4 multiplied by 10 to the power minus 5 meter square. Change in length equals delta L1 equals delta L2 equals delta L. Force applied in both the cases equals F. Young's modulus of steel wire is given by force into L1 divided by area 1 into delta L1, which equals F into 4.7 divided by 3 into 10 to the power minus 5 into delta L. Young's modulus of the steel wire is given by force into L2 divided by area 2 into delta L2, which equals F into 3.5 divided by 4 into 10 to the power minus 5 into delta L. On dividing 1 and 2, we get the ratio of Young's modulus of steel to that of copper is 1.79:1.